Hi all, we are now moved on to section 1.2, and this is going to be concentrating on acceleration and its applications, right? Specifically working on the application of how to quantitatively solve everything that we've been doing before. So we've been doing a lot of conceptual analysis and using different things like motion diagrams, position versus time graphs, velocity versus time graphs, and also also vector addition in order to create equations and understand how motion is. Now we need to actually do one final thing, which is work on acceleration versus time graphs. And then we're going to talk about, later on in section 1.2.1, we're going to talk about specific cases of free fall, which is up and down motion without an actual atmosphere. So falling objects through a non-atmosphere situation. And then what we're going to do is start application problems and actually do quantitatively solved problems, okay? So let's get started. What I want you to do is take a look at each one of these graphs below, and these are all acceleration versus time graphs, okay? So I want you to interpret each one of these situations and just kind of describe what you're seeing, okay? So take a moment and just talk and talk about what each one of these graphs are saying to you, and maybe write some notes. And then what we'll do is we'll go ahead and try to apply what we've learned to this new situation. So pause the video now and try it out. Okay, well, we're going to have to mark this up. So let's talk about this first graph. So what is this first graph saying? It looks like we have an acceleration versus time graph, and we have acceleration data in the lower part of the acceleration versus time graph, okay? And I like to put concrete numbers to things to kind of help me see what's going on. So if these are all accelerations, and the center line is going to be 0 meters per second squared, okay? And these are going to be all little seconds, so let's call this 1 second, 2 seconds, 3 seconds, and 4 seconds, okay? And let's go ahead and we'll call this a -3 meters per second squared. And what is this saying to us? Okay, so let's say at time 0, it's -3 meters per second squared. And at time 1, it's 1 second, it's 3 meters per second squared. And at time 2, it's -3 meters per second squared. And time 3, it's -3 meters per second squared. And time 4, it's -3 meters per second squared. Well, what this is saying is that the velocity is changing by -3 meters per second for every second, okay? And that change in velocity is the same across 1 second, 2 second, 3 second, 4 second. So what is this saying? Well, what this is saying is that we have a leftward pointed acceleration vector, okay, that is going to be pointed to the left at point 1, point 2, point 3, at time 1, time 2, time 3, and time 4. And all we know is that the acceleration vector is pointed to the left. Now from this, can you tell me if you are speeding up, slowing down, or constant velocity? Well, you can't. Without the added information of velocity, we don't know what this is saying as far as speed up, slow down, constant velocity. All we know for sure is that the change in the velocity is negative, okay? And here's what I'm saying. I'm going to fill in the area here. So in this graph, it's weird, just like the velocity versus time graphs, would talk about displacement, this acceleration versus time graph is talking about change in velocity. And when I talk about change in velocity, what I'm really talking about is the strict interpretation that acceleration is equal to the change in velocity over the change in time. Okay? And so what we know from this is that the area under the curve, and let's do dv dt, what we could say here is that the change in velocity is equal to the acceleration times the change in time, right? So I know I'm putting a little bit of calculus, and you may be college physics students, but what this is saying right here is that the area of the line relative to the 0 meters per second mark is the change in velocity. So what this is saying is delta V is going to be the area here. And what this is saying to me here is that the area here, it looks like this is a rectangle. Okay? And this rectangle, I'm going to erase some things, has a distance, has an area of 4 seconds, right? So this is a rectangle. So this area is a rectangle, and that is going to be 4 seconds minus 0 seconds times, so that's the length, and the height here is going to be 3 meters per second squared minus 0 meters per second squared. And I'm putting delta t and delta v right here, and that's the acceleration, right? Delta a right here. And so this would be the velocity. The change in velocity is going to be the area, which is a dt, right? The acceleration dt. So my point is that this is going to work out to be, so this area is going to work out to be 4 seconds times a negative 3 meters per second squared. And so what we know is that that change in velocity, which is the area, is going to be negative 12 meters per second. So what we know for sure is that overall, over this entire acceleration that was happening, even though it was a constant acceleration, it added, it made the, whatever the initial velocity was, even more negative by an overall negative 12 meters per second. So this negative 3 meters per second over 1 second was adding a velocity of negative 3 meters per second. It was adding a velocity vector. So at this time, what we know for sure is that it had a negative 3 meters per second. And then we're going to be adding this again. And now it's adding another negative 3 meters per second, and then another negative 3 meters per second, and then finally another. So it added an overall negative 12 meters per second to whatever initial velocity was there. Okay? And so these acceleration versus time graphs are very powerful because you could use them to actually just see what the overall change in velocity is. And if you knew that initial velocity, you could actually just go ahead and figure out its final velocity really quickly. You would just add it or subtract whatever this delta v is to that initial velocity. Okay? Well, let's go ahead and take a look at this situation. Again, if we go ahead and add numbers to this, 2 seconds, 3 seconds, 4 seconds, and in this case I'm going to make this positive 3 meters per second squared, right? So this is creating an acceleration. So this is a constant acceleration. At time 0 seconds it's positive 3 meters per second. 1, 2, 3, 4. So again, in this case, this is a constant acceleration vector, but in this case it's positive 3 meters per second squared. So this is going to be a rightward pointed acceleration vector. I want to make it the same size as the other one. Okay. And then what we could say from this area under this curve here, so this area here is actually going to be a positive 12 meters per second. Okay, so again, that delta V right here, this part works out to be a delta V. So that delta V is going to be the area under that curve relative to the 0 meters per second squared part, which is the area which is going to end up going, okay, so I'm going to now do an integral, and this is going to go from 0 seconds to 4 seconds, and that looks like a positive 3 meters per second. dt, which is going to work out to be positive 3 meters per second squared times t from 0 seconds to 4 seconds, which is now going to work out to be 12 meters per second. It'll be positive. Okay, so it's going to work out to be the opposite of this. I also want to point out in this case we used area to figure out the and it's actually kind of in a weird way a negative area, and so this area relative to the 0 meters per second squared part, okay, it's always relative to the 0 meters per second squared part, was a negative 12 meters per second, and then we used calculus to find this guy's area under the curve, which worked out to be a positive 12 meters per second. Okay, this last one is pretty cool, pretty easy. What is this saying? So this one is saying it's got a positive acceleration, this object has got a negative acceleration, and we could use the area to figure out the total change in velocity. But we don't know if it's speeding up or slowing down. All we know for sure is that its overall velocity is changing. Okay, but here, the acceleration here is 0. It's on the 0 meters per second mark. So what we know for sure is that the change in velocity, there is no area relative to the 0 mark, because this is 0. And so the acceleration is 0 meters per second squared. And then what we know for sure is that it's got a constant velocity. And that says something weird, because even a velocity of 0, what if the initial velocity was 0? Well, then that means the final velocity was 0, because there is no acceleration. And in a way, that is constant velocity. It could also be not moving. Okay, those are the two possibilities here, which are really the same possibility. And so these are acceleration versus time graphs. And we're going to be using a lot of acceleration versus time graphs when we get into forces. Okay. Okay, so we're going to go ahead and move on. And I hope you learned a little bit here. And so what I want you to do is I want you to take a moment, and I want you to actually try to just initially match, initially read this situation here. Okay, we have a cart that is moving to the right, so it's moving in the positive x direction, and so as it's moving in the positive x direction, it is slowing down. And so what you're supposed to do is match up these letters, these velocity versus time graphs, and these acceleration versus time graphs to this situation. So go ahead and take a moment and go ahead and do that. Okay? Okay, well, hopefully you paused the video and you had tried to match up the proper velocity versus time graph and the proper acceleration versus time graph for this situation. So in this case, well, actually, let's review for a moment. The definition of slowing down is when the velocity vector and acceleration vector are in opposite directions. So if you have a velocity vector that is to the right, that means its acceleration vector has to be to the left for it to be called slows down. slowing. Okay. Another situation could be that the velocity vector is to the left and the acceleration vector is to the right. That is also slowing down, but we're not really interested in that for this situation, because this situation is saying that is moving to the right, but it is slowing down. Okay, so this is the situation. The top one is what we're looking at. So we're going to be looking for a velocity graph where the green line is in the upper part of the graph, okay, but that green line will have a negative slope. Okay, so we're going to be looking where all of the green is in the upper part of the graph. Okay, so here we have a velocity versus time graph, and the green part is in the positive part of the graph, so it's got a positive velocity. But in this case, it has no slope, and a slope in a velocity versus time graph is the acceleration. Okay, this part, so A can't happen, so A is not correct for this situation. B is showing we have an initial velocity of initial positive velocity that is very low, and in the end it's got a high positive velocity, and that slope is positive, so that's going to be a positive acceleration. So this is, the top one is constant velocity. This one is speeding up in the positive direction. In the positive direction. Positive direction. Okay, let's try C. C starts out with a low negative velocity and ends up with a high negative velocity, and that slope is a negative slope. So this is speeding up, and the green line is in the negative part of the x-axis. So this is speeding up in the negative x direction. All right. Well, let's try D. So C is not right, B is not right. Let's try D. D starts out with a high positive velocity, and then in the end, over here, the final time is telling us it's got a low positive velocity. Okay, so that means all of that data is to the right, and that slope is negative. So this is slowing down. It's got a negative acceleration, and it's moving to the right as it's slowing down. All right, that might be it. I'm guessing that is it. Let's just double check. Let's finish everything. E starts off with an initial high negative velocity and ends with a low negative velocity. Okay, so this shows, and also if you look at the slope is positive here. So this is showing slowing down in the negative x direction. So it's moving to the left, but it's accelerating to the right. Okay, so E is not correct. So D does fit the situation. Well, now let's look at the acceleration versus time graphs. A negative acceleration is going to be a negative line. It's got to be below the axis. So right here, number 1 shows an acceleration that is below the line, and so it's a constant acceleration, which will go with a straight line here. This will be a straight line here. Number 2 is showing a positive acceleration. That is incorrect. And number 3 is showing an acceleration of 0. So D goes with number 1. All right. How'd you do? Let's try another one. Here we have another cart that is traveling in the negative x direction. So it's got a negative velocity, and it looks like it's speeding up as it's moving in that direction. So please go ahead and pause the video and try doing this. Okay, start off maybe by drawing your acceleration vectors and velocity vectors. Okay, and let's see how you do on this one. So try to match up the letters to the numbers and pause the video now. All right, we're back. Well, this object is moving to the left, so it's got a negative velocity vector. and it's speeding up, which means its acceleration vector is also to the left. Okay, the definition of speeding up is when the velocity vector and acceleration vectors are pointed in the same direction. So this is speeding up in the negative x direction. Speeding up in the positive x direction would mean both of those vectors are pointed to the right. Well, this is actually showing this is not applicable to this situation. So we're just thinking about this one, okay? So we're going to be looking for a green graph. We're going to be looking for a green line that is in the lower part of the velocity versus time. That'll show all of the velocities are in the negative part. And that the slope of the green line should be negative, which should be like this. It should be down and to the right, okay? Well, the only one that kind of fits this situation seems to be C. It starts off with a low negative velocity and ends up with a high negative velocity. And this is the negative acceleration that we're looking for. So this is showing that all of our velocities are negative. It starts low and starts to speed up as it's moving to the left. And it's got negative acceleration. So this looks like it's going to be our answer. And curve fit wise, this would be saying that we have a negative initial velocity and we have a negative acceleration times delta t. Incidentally, x final equals x initial. I don't know what the initial excuse me, the initial position are, but the initial velocity is going to be negative t delta t minus 1/2 a t squared. So that would be the curve fit for the position versus time graph. Well, if an object has a negative acceleration, then what that tells me is that the acceleration over here has to be in the negative part of the graph. Okay? And what that is saying here is that has to go with number 1. Okay? So this is how to apply acceleration versus time graphs to a given situation. Okay. All right. Well, let's try some problems. So let's try a problem where you have to apply what you've learned and interpret motion based on what you think is going to be happening. And we're going to try to use acceleration versus time graphs to solve for this. Okay. So here you go. You're going to give a ball an initial velocity that is going to be up a ramp, okay? So you're going to give it an initial velocity that is up a ramp. And it's going to go up this ramp, okay? And what do you think is going to happen to its motion as it goes from the bottom of the ramp? You've given it a high acceleration, a high positive velocity, initial velocity. And so it's not this problem, it's not going to fall off the ramp. It's actually going to go up the ramp and then come to a stop and then come back down the ramp. So what do you think is going to be happening as far as a velocity vector? Okay, so go ahead and just take a moment and think about that. All right, and then we'll talk about it, and then I'll have you choose which acceleration versus time graph you think mentions the situation. Well, okay, so pause the video now and try explaining what's going to happen to the velocity over the entire cycle of its motion. All right. Well, as you can see here, let's just say this, that we've got a little. We're going to have a little motion cart right here. So we're standing right behind this guy. Okay. And so we're standing right here looking at this. And this ball is going to go up. As it's moving up, it's going to be slowing down. So its velocity vectors are going to get shorter and shorter and shorter. And then right here at this point, it's going to come to a stop. Okay? And then what's going to happen is it's now going to start going the opposite direction, and it's going to start speeding up as it's moving downhill until finally it gets right to where it started, and its velocity vector that it started out with is going to be coming back as its final velocity. Okay? So what does that tell you if something is moving in the positive x direction, and I'm actually kind of twisting my coordinate system. So the x direction is parallel to the plane of motion, and positive x is going to be up and to the right, and negative x is going to be down and to the left. Okay? So this object is moving in the positive x direction. Okay, so I'm going to put this plane right here. Here's the origin, 0. It's moving in the positive x direction, and it's slowing down as it's moving in the positive x direction. So which one of those graphs would look like that if it's moving in the positive x direction and it's slowing down? Would it be A, B, C, D, or E? Well, it's going to have a high positive initial velocity, and then it's eventually going to come to a stop. So it's going to have a 0 velocity. So it's that first part of the motion is going to look like this. Correct? And then what's going to happen now? Well, now it's going to come to a stop, and now it's turning around. So its a velocity at this top part is equal to 0, right? So it's got an instantaneous velocity, but now it's turning around, and now it's going to be traveling in the negative x direction, and it's going to be speeding up as it's traveling in the negative x direction. So in a velocity versus time graph, what does that look like? If it's so D was the first part, well, C is going to be the next part, right? Now it's going to be traveling in the negative x direction and speeding up. As it's speeding up. So that's kind of interesting. This D is going to be the first part of the graph, and then the graph is going to continue looking like V. Well, let's make a velocity versus time graph so we could show you what it looks like here. And this is velocity is equal to 0. This is a positive velocity. This is a negative velocity, okay? And this will be the initial velocity, and this will be the ultimate final velocity here. The initial velocity is this green one. The negative final velocity is this bottom one, okay? So here we go. It's going to start off with a high positive velocity, and then at the top part here, it's going to come to a stop, and then an equal time later, it's going to have a very negative velocity. So its velocity versus time graph is going to look like a straight, that horrible line. Let's try it. Straight, somewhat straight line. And it's going to have a positive velocity, goes to 0 at the top, comes to a stop, and now it's turning around. It was moving in the positive x direction, and then it comes to a stop, and now it's moving in the negative x direction, even though all of its positions were positive. Now describe this graph, okay? What is the slope of this line? Does it change its slope at any point, or is it a constant acceleration? Well, if you notice, it's a straight line, so that's a constant negative acceleration, right? So which one of these graphs would fit this part, right? Which one of these graphs would describe this constant negative acceleration? Okay. Well, D would, right? It's got a negative acceleration the entire time. And I want to add something here, which is very weird. That, well, not weird, it kind of makes sense, that at the point where the velocity is 0, which is at this halfway point, it has a negative acceleration. So when an object has an instantaneous velocity of 0, but it has an acceleration, that usually happens when the object is turning around or changing directions by 180 degrees. Meaning it was traveling up and to the right. now it's traveling down and to the left after that motion. Well, for that to happen, it had to come to a stop at some point in between both of those. Okay, so this is how you apply acceleration versus time graphs and interpret motion. So we had talked a little bit before about the area under the area relative to the 0 meters per second mark of an acceleration versus time graph, right? And we had said the area under an acceleration versus time graph is the total change in velocity, or delta V. Okay, so that is the area underneath area relative to a 0 meters per second squared acceleration. Okay, and sometimes that can be a negative area, it could be a positive area. Okay, well, we're going to try to apply what we've learned. Okay, here we go. We have a graph that shows the acceleration of a particle with an instantaneous velocity of 10 meters per second. Well, with an initial velocity of 10 meters per second. What's the particle's velocity at the 8-second mark? Okay, so we have to find the final velocity at this point. Okay, so how do we do that? All right, well, we know the initial velocity at the 0-second mark, VI, is equal to 10 meters per second. 10 meters per second, okay? And that we know the final velocity is what we're trying to solve for, and this is over a time period of 10 of 8 seconds, right? But if you notice, there's two accelerations happening here. In this first part, this object has a positive 4 meters per second acceleration, and this is an acceleration versus time graph. So it's got a positive 4 meters per second squared acceleration. And then at this point, it's got a changing acceleration, which we typically don't study in our class, but now this looks like this acceleration is changing by what? 4 meters per second over the period of 2 seconds, right? So that's, I'm thinking rise over run. It's going to end up with so this guy right here has a 0 acceleration. So that slope is going to be rise over run. So it's going to stop here at 0 meters per second squared, and it started out at positive 4 meters per second squared, and it did that from 8 seconds, from 4 seconds, right? So that slope is going to be negative 4 meters per second squared over 4 seconds, which is going to work out to be negative 1 meters per second cubed, which is called a jerk, by the way. That is called a jerk. When your acceleration changes with time, that is called a jerk. Anywho, so this guy has a change in its slope, okay, so this is a constant acceleration at this point, but now its slope, I should do this, I'm going to just be careful here. That this, I want to put on the slopes here, that this slope right here, which is a jerk, is going to be 0 meters per second cubed, and this slope is going to be negative 1 meter per second cubed. Okay, well, we could actually apply what we've learned as far as area under the curve, right? So the acceleration is going to be delta V over delta t, right? Which is the same thing as dv dt. And so dv is going to be equal to the acceleration dt, and this is the area under the curve, right? And so if we know that change in velocity, all we have to do is add that change in velocity to our initial velocity of positive 10 meters per second. So delta V, if we add that to our initial velocity, that should be our final velocity, right? Right? If delta V is V final minus V initial, right? And we add that to V initial, isn't that just the final velocity? Right? Negative VI plus VI. So what we're going to do is we're going to find this area under this curve for this entire thing using a rectangle and a triangle, and then we're going to go ahead and double check it with our calculus. Okay, so here we go. What is the area of this rectangle right here? So the area of this rectangle right here is going to be 4 meters per second squared times 4 seconds. So this is going to be 4 meters per second squared times 4 seconds, right? Which is going to be 16 meters per second. All right. And this guy here is a triangle, which is going to be 1/2 the base, which is 8 minus 4. 8 seconds minus 4 seconds, times the height, which is 4 meters per second minus 0 meters per second. 4 meters per second minus, squared minus 0 meters per second squared. And so this is going to be 4 times 4, 16 divided by 2, which is going to be 8 meters per second. So the total area here, or the total delta V, should be 16 plus 8 should be 24 meters per second. So if we started out with an initial velocity of 10 meters per second, and we then are adding to that a positive 24 meters per second, then the final velocity should be, something like positive 34 meters per second. That should be the final velocity. But let's just check the other solution here. So here's what they did. They did basically the same thing that we did. They said the area under the curve between 0 and 8 seconds is just a rectangle. And then they add to that the area of the triangle for this part. Okay. And they then added that to the initial velocity. And so they added that change, that here's the rectangle and here's the triangle, and they added that to the initial velocity. What I want to do real quick is, while we're here, I want to snip this and create a new whiteboard, and let's try it with calculus. So we're going to do this problem, but we're going to apply our curve fits. Okay, so I'm going to snip this, and we're going to do this again, but we're going to try it to do it using calculus. Okay, so even though we know the answer is correct, okay, I want to show you how to do this using equations in calculus. All right, so in order to do this, we're going to actually have to create two equations. Okay, so for the time being, this first part here, we're going to call this part 1, and this is part 2. So to get the change in velocity for part 1, we're going to have to do a fit, a linear fit, and so excuse me. We're going to be predicting the final acceleration, right? It's given an initial acceleration plus the slope delta t, right? And again, I'm just doing y is equal to b plus mx, right? So that's our basic equation. But in this case, our y axis is acceleration. Our initial data point right here, which is 0.4 meters per second squared, that's the initial acceleration. Slope is going to be a jerk, and a jerk, again, is going to be jerk is going to be change in acceleration over the change in time. Okay, so that again is a jerk. All right, which is the slope in an acceleration versus time graph, and this is delta t. Well, to predict the final acceleration from 0 seconds to 4 seconds is what we're going to be doing in this first part, which means we start off with a positive 4 meters per second squared plus the slope, which is 0 meters per second cubed, times delta t, which is going to be 4 seconds minus 0 seconds. All right, and so that line is going to be positive 4 meters per second squared. Okay, so that is the acceleration for that part. Well, now we have to apply some calculus. All right, so again, acceleration is equal to dv dt, or in other words, it's equal to delta v delta t. And so delta v is equal to acceleration dt, and that we're now going to be applying our limits to this. V initial, V final, dv is equal to our change in time, and in this case our time is going to be 0 seconds minus 4 seconds, and our acceleration here, which we've determined, is going to be 0.4 meters per second squared dt. And so this part right here, that part is just delta v. And so I'm going to just write that here, delta v, and that's going to be equal to positive 4 meters per second squared t from 0 seconds to 4 seconds. Okay, which is going to be 16 meters per second squared, 16 meters per second, and this is minus 0 seconds. So this is going to overall, this change in velocity for the rectangle part, for part 1, is just going to be 16 meters per second. And that's going to be from the 1 to 4 second mark, or 0 to 4 second mark. For part 2, okay, we're going to now do a prediction equation for that. Okay, so this is predicting the final equation for that, and that's from 4 seconds to 8 seconds. Okay, and so that final, so I'm just creating a linear equation for that I'm going to plug in to our integral. And so that starts off at positive 4 meters per second squared is our initial acceleration. But our slope, which we determined earlier, is going to be negative 1 meter per second cubed delta t. Okay? And so that is a linear equation that describes this part of the line from 8 to 4 seconds. And so our delta v is going to be equal to 4 seconds to 8 seconds of our equation, which is 4 meters per second squared, minus 1 meter per second cubed t dt. And so when we work that out, and I need to give myself a little bit of room here. What we got is we're going to integrate this first part, which is just going to be positive 4 meters per second squared times t, and this next part is going to be negative 1 meter per second cubed over 2 t squared, and that is going to be from 4 seconds to 8 seconds. Okay, and so delta v for the second part, and that's this is for the second part, and this is delta v for the this is delta v for the first part, this is delta v for the second part, for 4 seconds to 8 seconds is going to be 8 times 4. So I'm going to do this. Positive 4 meters per second squared times 8 seconds minus 1 meter per second cubed divided by 2, and that's going to be 8 seconds squared. And so I just applied the top part of the integral, and now I'm going to apply the bottom part of that integral, which is going to be positive 4 meters per second squared times 4 seconds minus 1 meter per second cubed over 2 times 4 seconds squared. Okay. Well, I'm going to have to use a calculator. Sorry. So, this is 8 times 4. 4 times 8 equals 32. So this part here is going to be 32 meters per second. And this is going to be 64 divided by 2, which is also going to be, let me just make sure I didn't make a mistake, 8 times 8 equals, and that's going to be divided by 2. And that is also going to be 32 meters per second. So this first part is 32 meters per second minus 32 meters per second, which is going to be 0. And this next part is going to be 16 meters per second squared. So 16 meters per second squared. So let me redraw that again. Okay. This is going to just be 8 negative. So yeah, 4 times 4 is going to be 16 meters per second. Not squared. And this is going to be 4 squared times 1/2, so that's going to be negative 8 meters per second. And so this is going to be 0, and this is going to be 8. So this is going to work out to be 8 meters per second. And so that delta V for part 2 is going to be 8 meters per second. Okay, so you're going to have 16 meters per second and then 8 meters per second. So overall, so that total area under a curve, so delta V total is going to be 16 meters per second plus 8 meters per second. It's going to work out to be 24 meters per second. And so adding that V total to the initial velocity is going to work out to be 24 meters per second plus 10 meters per second. And then again, we're going to get 34 meters per second as the final velocity. And I should have erased this V total. Well, actually, should elaborate. This is going to be V final, right? Because again, V final minus V initial plus V initial is this part right here. So it works out the same. Okay? Well, now we have a better view of what is happening with our graphs, right? If you have a position versus time graph, okay, and you differentiate that with respect to time, differentiate the x equation with respect to the prediction equation for the curve fit of the position versus time graph with respect to time, you get a velocity versus time graph, right? And you get this new equation. Well, if you differentiate that with respect to time, which is right here, you get an acceleration versus time graph. And now, given an acceleration versus time graph, if you integrate that with respect to time, if you integrate that with respect to time, you get the velocity part, which is a velocity curve fit. You just need to know what the initial velocity was. But then if you integrated that again with respect to time, you would now get the position versus time graph. You would get displacement, which is the position versus time graph. So now we have a better view of what is happening with our graphs, okay? And so that's how we're going to be using our calculus to create, you only really need to capture one of these. If you can do a velocity versus time graph, you could then integrate that with respect to time, and you could get the displacement. And if you differentiated that with respect to time, you would get the acceleration. So really, once you have one of these, you could just differentiate it or integrate it, and you could get all of the others, okay? So calculus is a really powerful tool that we're going to be using in our kinematics equations. So next off, we're going to be talking about free fall. Okay, so I hope you enjoy it, and we're going to be moving on to free fall and then actually do some quantitative and application problems. All right, talk to you later.